Now we're going to talk about the total sum of squares, the regression sum of squares, and the error sum of squares. Okay. By the way, before we get started in this, note that some books use SSR, or some books write this as RSS. Some books actually write RSS to mean residual sum of squares, which is actually this thing. So it gets really, really confusing. If you jump to another book, just note that these symbols, these acronyms here, change, and it gets real confusing. You'll just have to be aware of that if you jump to another book. All right, so we have this thing called the total sum of squares, which is, take a look at this. So these are our response values minus mean squared summed up. Okay, then we have this thing called the regression sum of squares, which is, look at this. You get it's the sum of the squared deviations between the predicted values minus the mean. And then we have an error sum of squares, which is the sum of squared deviations between the actual observed y values and the predicted values. Now let's see if we can make this make some sense here. See if we can make this make some sense. I'm going to turn my paper to the side for a second here. Now, look, if you just have one variable, and let's say maybe you make some observations on that variable, and here they are. It's a quantitative variable. Okay. Maybe we'll put another one right there, and one right there. Okay. All right. This is we'll let this be we'll call this our y variable. Okay. Where's the mean here? I'm just eyeballing this. Probably right there. There's our sample mean. Okay. One of the main goals of regression is to try to explain the behavior in one variable in terms of another. And also, we'd like to explain the variation in these observations in terms of another. Maybe there's some other underlying variable here that's explaining the variation here in these data points. Maybe this point was far to the right because it was really hot that day, and maybe this point wasn't as far to the right because it wasn't as hot that day, and maybe this point was really fell to the left because it was colder than average that day, or something like that. Okay, so that's sort of the idea. There's a variance associated with this, and by the way, if you don't know the variance of a random variable, this is just defined to be, it's the sample variance anyway. It'll be the sum of well, let me write it like this: the sample variance of this random variable y. Okay, sample variance. It'll be the sum of the squared deviations from the mean over n minus 1, right? That's the sample variance. Now, if I take the square root of all this, I get the sample standard deviation, right? But sometimes we don't do that. We just look at this quantity. Perfectly fine. The sample standard deviation and the sample variance both just measure some, there's some kind of a measurement of spread outiness about the mean. Okay, the smaller it is, the more clustered in towards the mean they are, and the larger the variance or standard deviation is, the more spread out away from the mean they are. Okay, you know what I could do is maybe I want to disregard this and just just look at the sum of squares. Okay, so then this is no longer the sample variance, but it's still just an overall, some kind of overall measurement of squared, some sort of measurement of spread outiness about the mean, isn't it? Okay, it's just not sort of averaged by the degrees of freedom there. Okay, so that's what all these three quantities are. Now let's take this. These data points here, and let's say we have something like this. Okay, okay. Now maybe here's the here's some other variable x. Here's y. Okay. Maybe I've discovered that there's some other variable here, like temperature. Okay, and it looks like as the temperature increases, goes to the right, that this other measurement, whatever it is, maybe it's volume or something, maybe we're tracking volume versus temperature of a gas or something, that the volume, the trend is to increase. Now, I still have the same average, right? This is y bar. Okay, and you can see what I've done here is I've sort of, this one goes with that one, this one goes with that one, right? And this one goes with that one, and this one goes with that one, and this one goes with that one. We've just entered another variable in our model. Okay, so it turns out, maybe it turns out, I don't know, that a regression line that would run through these points, maybe the best fitting line is say right there. Okay, so I'll just denote that here. This is our y hat equals b1x plus b naught. Maybe that's our best fitting regression line. So what is this SSTO? Look at it. It's the sum of squared deviations from the actual observed y values off of that average line. So here it is. Let's see. Let me just, these are the deviations, the signed deviations. Got 1, 2, 3, 4, 5, 6, 7 of them. Okay. If I square them, look at what I get there. I get squares, right? And then it says you add them up. Okay. So you add up all the areas in those squares, right? And that is what SSTO is. It's sort of an overall variation measurement. It's a sum total variation measurement off of this average line. Note that it has nothing to do with the regression line, and it has nothing to do with this x variable down here. Okay? It has nothing to do with this x variable. The idea now is to see if we can break up this this total variation off of this y average line by introducing this red line model. So here I'm going to color code this. SSTO, this will be black. SSR will be red. And in a minute maybe we'll do this SSE stuff. Well, maybe we'll do that in green. All right. SSR, this is the sum of square deviations from the predicted values, or the regression, the fits, right, from the regression line, minus the average y value. Okay, so so for this point right here, its fit turns out is real close to it. It's right there. Okay, so I'm going to go from, so this is the y hat value. The y hat values are on the line, right? Minus there. Okay. So this is a little smaller, isn't it? Okay, and then the fit for this one, however, is a little larger. So I'm going to come in like this. The fit for this one, whoops, let's see. Didn't do that right. Sorry. Think. There we go. Should be like this. Geez, need some whiteout. Remember that stuff? Whiteout. Okay. Sorry. I'll try to do the rest of them correctly. Here's the fit for this point right there, and then it comes down like this. All right, I got to pick up this square here. The fit for this point is actually up here. I drop to the line, and I get this area. The fit for this point is right here. It looks like, oh wow, that okay, it's right there. The square has basically no area. The fit for this point is down here. Drop to the line. Okay, the fit for this point is right here. Drop to the line. Okay, and the fit. Okay, well I guess we're done. Now, sorry about this mistake here, but if you add up these areas in red and compared to the areas in black, well, it's smaller, isn't it? Yeah. Okay, so that is hopefully this you actually want these areas in red to sum up to be as much as possible. It turns out that they will never be as large as SSTO, but you want them to be as large as possible, because the idea is that this SSR is sort of it's sort of the amount of total variation that in the data that the regression line, that this best fit line is accounting for. Okay. Finally, let's look at SSE. What's that? SSE is the sum of squared deviations between the y values of the observed points, the observed responses, right, like this guy, minus here, right, the fit. Okay, so, and I'm doing that. Okay, I'll go to this one. This one goes to fit there, like that. Okay, and this one goes to, let's see, to there, right? This one's about the same. Look at what happens on this square here. It looks like the black and the green are the same. That is because the regression line is running right through that y-average point. Okay. Let's see. What about for this guy? And take the y value minus the fit. Okay. It's there, and you keep on progressing this way. Okay. Look at this. This guy's pretty small. That's what you want. You want these things to be small. You want the green squares to be small. Okay? That's because the green squares are the sum of squared errors. It's the sum of the squared deviations. It's sort of an overall measurement between the response and this new model. See, before this was our model essentially. We were tracking one variable. Now we've sort of blown it out into another dimension, this x dimension here, and we want to track and see if by introducing this new variable we can explain more of the variation in our data. And so if these green squares are small, then these red squares will be big, and vice versa. It turns out, and here's a fact, that the total sum of squared errors partitions nicely as the sum of the regression sum of squares and the error sum of squares. Okay. In our regression modeling, we like for this to be small. Okay. Because when that stuff is small, which by the way is the green stuff up here, it's the total sum of the green stuff. When that stuff is small, then look at what that means. It means that our regression line in red is actually coming pretty close to our actual data points. Okay, and because it partitions this way, this is an algebraic fact, you can prove this, because it partitions this way, if this is small, as this goes to 0, this SSR approaches SSTO, okay, which is nice. You want this SSR, this regression sum of squares, to be as large as possible. It sort of measures the total variation captured by your regression line model. Okay, but this is not obvious. This is not obvious at all, at least not to me. But you can prove this algebraically. Okay, as you vary the explanatory variable, that is, the x variable, you'd like to know to what extent it seems to explain this variation in the response variable. One way to do this is with this so-called coefficient of determination, or r squared. Okay, r squared is defined to be its SSR over SSTO. Okay, and like we said on the previous page, it turns out that SSTO partitions as SSR plus SSE. Now, this quantity is always, at least 0. And this quantity is always at least 0, and this quantity is always at least 0. You can tell that by looking at the formulas for them, right? Because they're sums of squares, and squares are always positive, and sums of positive things are always positive. So each of these quantities is always non-negative. So r squared is always going to be non-negative. Look at what this is. Remember, we said that SSR is sort of some overall deviation measurement. It sort of explains the sum total variation in our regression line, or the sum total variation that our regression line explains in our data. if I take this quantity and divide it by the total, it sort of should be kind of a, maybe that's kind of like a overall percentage of variation in our data that's explained by the regression line. Sure, that's exactly what it is. And another way to write that is 1 minus SSE over SSTO. You should be able to see that using some simple algebra. But this is r squared. It turns out that that r squared is indeed little r squared. Remember that little r was defined to be 1 over n minus 1 times the sum of the products of the z-scores in the x and y directions, right? Like this. Okay. It turns out that in fact, if you square all this mess, you'll get this. Okay. It takes some doing, but yeah, that's exactly what it is. Now you have to be very, very careful here. There's a big word of caution. I'll draw you a picture here to illustrate this, but this coefficient of determination, r squared, is not necessarily a good way to evaluate a model. Oftentimes, researchers, professors, and so forth, they'll be doing some statistics, and they'll get r squared, and if it's really high, then they'll say, yeah, the model's great. Okay, surely, if you have a situation that it looks like this, maybe if I have some data points that kind of go like this, ignore this one. We'll throw this one out. Okay, sorry, that's a mistake right there. Just forget about it. Yeah, so if I got a regression line for these values there, it's probably going to go like this. And what do you bet the r squared value is probably pretty high? It's probably like 0.98. Okay, r is probably like it's close to -1. Okay, because it has this line will have a negative slope. But what happens if I go and I find another data point and say, oh, you know what? I forgot about this guy way up here. Okay, and if I redraw this regression line, look at what's going to happen. I'm sure of this. I know from experience. This line has a leveraging effect. I'm sorry, this point has a leveraging effect on the line. Okay, r squared is probably still going to be pretty high, like 0.95 or something. Okay, but it's really probably not a very good model over this entire range from from where x equals say 0 up to whatever this coordinate is, because probably a better model is or sort of remains to be seen, but it might be something that's parabolic, okay, or it could be that this point's an outlier and you want to throw it out anyway. What you really would have to do is come in here and take data points down in here to see really what the an appropriate fitting model might look like. But be careful of that. Just because r is really close to 1 doesn't necessarily mean that the model is really good at all.
Okay, so let's take a look at an example. Let's pull up those data that we had before on the 10 used cars. I'm going to, since I've started a new R session, I'm going to just recreate all that. Okay, I'm storing I've got my ages and years and my prices in $100 bills. Okay, remember you can see age and price that way. I'm going to use that linear model function, that LM function, to build a linear model that attempts to predict price based on the age. Okay, so there we go. And now, if I do summary of linreg, then I'll see a whole lot of output. Okay, we've seen this kind of thing before. Here's my intercept. It says that when the age is 0, the price is roughly 200 times $100, and it looks like the age or the the slope estimate is negative 12.152. So multiply that by $100. That's negative 1215 approximately per year. Looks like what that's essentially saying is that the price of a car is depreciating at a rate of about $1,200 per year, according to our model. You see all that output here in the notes. This multiple r squared value is that r squared value that we were just talking about in the notes. This is the coefficient of determination. It's fairly high, okay, 84.59%. That's really pretty good. Okay, again, this adjusted r squared, we'll talk about it later on, but it's also an indicator of goodness of fit for the model. Another way, if you just wanted to get the r squared value by itself and you didn't want all these other this output, note that this summary ln-reg stuff is actually it's a large object in R, and when you put a $sign there, it'll spit out whatever part of that object that you specify. So sometimes if you're dealing with a matrix or a data frame, you might put the name of the matrix or the name of the data frame here to the left, and when you put $sign and then stuff to the right, you indicate which variable that you want to look at or which column you want to look at. Okay, so this number is, in fact, it's just this number. It's just not rounded. Okay, that is the multiple r squared. Now, let's suppose that we find another data point, say a car that's 55 years old selling for $99,000. Okay, which that's not too unreasonable, I think, right? Cars that, if they reach a certain age, they even begin to go up in value depending on the make and model and how much they're sought after, if they're a collector's item, whatnot. So let's just add this point to our data set and then reevaluate. So I'm going to create this data frame called used cars, or I'll abbreviate it with UC. Okay, and the first column in that data frame will be age, and the second column will be price. Okay, so you can see what it is there. That's just a data frame with our age and price variable. But now I want to add a row. You can do this by saying that I want to go to the data frame called UC and put a left and right bracket, and on the left side I'm going to this position here I'm going to indicate the row, comma, indicate the column. So in the 11th row, first column, I'm going to assign a 55, and then similarly, have to use a square bracket there. In the 11th row, second column, I'm going to put in a what's it, 990? Yeah, because remember our units there are $100 bills. So 990 $100 bills. It's $99,000. Okay, now if I type UC, I'll see that there are in fact 11 rows, and that 55 990 point is included. Okay, so that's a simple way to append a data set if you just have one or two data values to add to it. Now I want to make a plot of I could do by the age and price variable. There are lots of ways to do this, but look at the way I'm going to choose to do it this time. Just because that's just because I'm putting my my y variable in first, comma x variable. Okay, look at how I've indicated that. My y variable here is I'm going to the column in my UC, or used cars data frame, and I'm going to the second column. By leaving this row position blank, it says we want all rows. Okay, all rows, second column. Okay, so it's looking at these, comma, my x variable then will be age, which is similarly, I'm looking at the UC data frame, square bracket, all rows, left that blank, put a comma there, first column. Okay, and there we go. So you can see what has happened. This is this is not out of the question. This sort of looking graph. It could be that cars actually, car prices behave like this, right? You might expect them to depreciate for a little while, and then over time, suddenly they jump back up again. Okay. Um, let's do a linear model now for the new data set that includes that far out point. We might even call that an outlier, right? Because it lies out and away from the rest of the trend, from the rest of the pack there. Okay, so I'm going to do linear model, and just going to let the output of the linear model be stored in something called out, and summary of out. Okay. You can see that things have changed substantially, right? Our intercept now is different, and this is our slope, 16.72. Our slope is now positive. It was even negative before, indicating depreciation. Now it's positive. Okay, and our R squared value it has even increased. It's over 90%. Okay, so if you weren't looking at the picture, you might think that the model has actually improved, right? Because because the R squared value has gotten higher. Okay, but like we said though before, that this probably what you would want to do here is probably, in order to really get a good model for this overall large picture, you really need to take some data values down in here. Okay, get some. Hey, you know what? We have got things reversed, haven't we? Looks like we've got the prices down here and the ages up here. Let's redo that. I'm going to do plot. See how easy it is to change your errors there. Now, if I wanted to preserve that original plot, remember I could use the Windows command like that, and then it'd create a new window there. Maybe I'll do that. Okay, there. See. There we go. Okay, now that looks right. I've got my age down here on the horizontal axis and the price going vertically. Okay. Still, though, I think this is the correct output. Okay, the intercept is 27.2. It's coming down, down in about there, and the slope is positive, about 16.72. Okay, I think that's about right. Okay, but so anyway, the idea here is that a good linear model for predicting price versus age down in this region would probably be our original model running down through this way. But to get a good overall model, from 0 to say 60 years, you really need to observe some prices and ages of cars in this region, and probably it's not going to be a linear model. It might be more parabolic in nature, which you can build, and we'll cover that in this course.